Hello, welcome to our capstone project. My name is Sebastian Simic.
I'm Lindsay Colchis.
And we are two members of Feed Forward Design Group. We have collaborated with Emerson Electric to investigate the transition from a natural gas market to a hydrogen market. Unlike conventional power generation from fossil fuels, which emit greenhouse gas emissions and other pollutants, hydrogen combusts to form water vapor only. Hydrogen may also be generated much more purely than natural gas, which means that many secondary pollutants to carbon emissions, like SOx, VOx, and particulate emissions, can also be eliminated. Hydrogen power plants are more expensive than the status quo in the short term, but show significant promise to reduce in cost over the next 10 years, and the hydrogen economy as a whole has the potential to grow to a $2.5 trillion market by 2050. To achieve this domestically and internationally, significant investment in manufacturing, scaling production, and creating a sustainable market demand is necessary. A critical design decision in this project is to produce blue hydrogen or green hydrogen. Blue hydrogen is produced via fossil fuels with carbon capture, while green hydrogen is produced via electrolysis with electricity produced by renewables. Long-term, green hydrogen is expected to be the dominant production method. However, it is not expected to be economically competitive until sometime in the 2030s. Blue hydrogen, on the other hand, is much cheaper to produce and serves as a great candidate for hydrogen production until the electrolysis method becomes more competitive. We have decided to make blue hydrogen in an effort to make this process as economically competitive as possible. Our process consists of 3 stages: hydrogen production through chemical looping reforming and the water-gas shift reaction, hydrogen purification and carbon capture through solvent-based adsorption technologies, and finally energy production through a cogenerative 2 turbine and steam process.
The chemical looping reforming component includes an air reactor, fuel reactor, and downcomer between them. Air and an oxygen carrier, such as perovskites with 5% nickel oxide in our case, are fed into the air reactor. The oxygen carrier binds to the oxygen in the air and nitrogen is eliminated. This oxidized metal now brings purified oxygen through the downcomer to ensure no mixing between the air and fuel reactors. Once it reaches the fuel reactor, methane and water are fed into the reactor to partially oxidize methane to produce syngas, carbon dioxide, and water, while the oxygen carrier gets recycled and reoxidized for a continuous process. The syngas, carbon dioxide, and water is then fed into the water-gas shift reactor, which in reality is a bundled tube reactor with packed copper oxide particles, but is modeled as a plug flow reactor. Each control volume exists in equilibrium reaction pushing towards the products of carbon dioxide and hydrogen gas, purifying the stream to our target products and eliminated the unwanted compounds. The carbon dioxide and hydrogen gas is then sent to a solvent absorption process, where they are fed into an absorbing column at low temperature and ambient pressure. The lean solvent enters the top of the packed column and flows downwards. As gas rises through the column, carbon dioxide is chemically absorbed into the solvent, bringing it from the gas phase to the liquid phase. The purified gas then leaves the top of the column consisting of hydrogen and water. The CO2-rich solvent then leaves the bottom of the column, is heated and pressurized, and passed through the stripping column, where CO2 is desorbed from the solvent and is captured at the top of the column as a high-purity gas. The lean solvent exits out of the bottom of the stripper, is cooled, and then recycled back to the absorber column for reuse. The carbon dioxide is captured and sequestered, while the gaseous mixture is flashed to remove the water and pure hydrogen gas is left. This hydrogen gas is then fed into the turbine. Air first enters and is compressed during the compression phase. Hydrogen gas is introduced during the combustion phase to make energy and heat, which is used to power our grid and feed our cogeneration plant.
Our process was simulated using Aspen Plus, and the following slides show the chemical looping reforming, water-gas shift reactor, solvent absorption, and turbine and cogeneration portions of our simulation. With our process, approximately 77% of the CO2 was sequestered from the solvent-based absorption. We are currently performing an overall cost and life cycle analysis to better understand the great magnitude of this transition to a hydrogen economy.
We'd like to thank you for coming to our booth, and we look forward to hearing any questions or comments you have.